Now that we're comfortable vectorizing our text, we're ready to jump into the really exciting field of topic modeling. Topic modeling takes a set of documents, and by documents, I mean individual pieces of text. So this could be rows in a data frame with your text in, it could be items in a list, anything like that is just referred to as documents. Topic modeling will scan each of our documents to identify patterns. We can then group similar documents together into our topics. If you take your mind back to section 1, you'll remember we discussed supervised and unsupervised machine learning. Topic modeling is an example of unsupervised learning. We don't need any labels in our data to find these topics. The algorithms work by just identifying key patterns. The algorithms work by identifying similar word patterns throughout these different documents. From there, these word patterns are used to identify what each piece of text is talking about, and once the algorithms understand this, they can group similar documents together really easily. Let's illustrate what these different topics might look like with an example. Let's take the following piece of text. AI is now able to create videos and audio that are hard to distinguish from the real thing. Recently, a number of celebrities have been impersonated, and journalists need to take extra care verifying sources before going to publication. You don't need any special hardware to work with AI. Governments are discussing bringing in regulations and policy. So when you look through this text, you might see that there are a couple of different themes that come out. One of the topics could be around equipment, so you've got the words video, audio, and hardware that you could bring together into one topic. You then have words like celebrities, journalists, publication that could form the second topic around media. There's also some words around government, so you've got the words government, regulations, policy. This could form a third topic. This is a really basic example of how topic modeling essentially works. It looks for key themes within our text, and then once it knows these key themes, it can give an overall theme to the document and identify similar documents together. Topic modeling is a great resource for any NLP data scientist. It can work quickly and identify key themes and patterns in our data. It can also take a large amount of text and find patterns that humans just might miss if we were to do it manually. There are a number of different algorithms in the topic modeling field, but we'll be focusing on the two most common today. The first, latent Dirichlet allocation, and then moving on to latent semantic analysis. Now let's move on to our next lesson and start putting this into practice. Before we go into our practicals, let's go through some examples of where you might want to use topic modeling depending on the kind of data that you've got and the work that you're doing. One really great way of using topic modeling is grouping things together such as news articles or research papers under different topic headings. If you've been on a news website, you'll often see that articles are grouped together under topics of what those articles are about. These topics can either be created manually by editors and curators, or we could implement topic modeling to identify themes in the text and group them together under those topics, thus speeding up the process and meaning a lot less manual work. Another example is where you have customer feedback or reviews data coming in. Most companies just don't have time to manually go through all of these reviews and this feedback and see what their consumers are saying. This is where topic modeling can jump in and save you so much time and energy, going through all these reviews and pulling out key themes about what customers are saying. Topic modeling can also be used for social listening, where we monitor social media data around our brand or our product or our company and be able to quickly pull out key topics that people are talking about in relation to our brand. These are just a few examples of topic modeling, but there's absolutely loads of applications you could put this in, and hopefully this lesson has given you some ideas of where you can implement this in your work. Let's now discuss latent Dirichlet allocation and exactly how this algorithm works. Let's take an example from the last lesson. We have a collection of news articles we want to classify into different topics. So this could be politics news, sport news, business news, etc. How do we decide which document is about which topic? Well, we can look at the words they use. So for example, words such as ball, player, match, game. If these words appear many times in the document, we can probably take a guess that this article is going to be about sports news. Some words are going to be more relevant to the topic, and some words can occur in more than one topic. So, for example, the word crash could be related to traffic news or financial news. We say that the topic is latent within the document. We must examine the words within it to discover the topic of that piece of text. A document can obviously contain words from more than one topic, but we make the assumption that it's mainly focused on a single topic with only a few words relating to other different topics. This is our Dirichlet distribution. So we have an understanding of what we mean by latent topics and our Dirichlet distribution. LDA then works as an iterative process, where we first specify the number of topics that we want as K. The first iteration of the algorithm is where words in the document are randomly assigned to one of the K topics. We then move to the second iteration, where we go through each individual word in the document. We assume that all other words are correctly assigned to a topic, and we try to correct the current words we're looking at's topic assignment. LDA corrects the assignment by looking at the proportion of words in the current document assigned to a topic, and the number of times that this word is assigned to a specific topic in other documents. The algorithm iterates through this process multiple times until it reaches a steady state. It then gives us the final topic assignments for us to investigate. Now let's go to our notebook and see what this looks like in code. So to run the LDA model, we're going to need to import the gensim package. So we can import that along with the pandas, RE and NLTK packages that we're going to need. Next, we'll load in our data. For this example, we're going to be using news articles. So we use pd.readcsv, newsarticles.csv. We then run data.head and we can see we've got an ID, a title and a content. So the content is just the content of the news article and the title is the title of that article. When we run data.info, we can see we've got 100 rows of data and we've got no nulls. Because we're just interested in the articles from this data set, so the content, we're just going to pull these out so they're separate from everything else. So we'll create our articles and then just pull the data content column. Once we've got our articles, we're going to clean these up a bit. I'll just copy this across. We've seen this in a lot of other lessons. So we are removing the punctuation, we're lowercasing, we're removing the stop words, we're tokenizing, and we're stemming. I've chosen to do stemming here because we have quite a lot of text. So it's going to mean that our processing times are going to be sped up quite a lot because we're able to shrink down quite a lot of the words. You can use lemmatization if you want, but for this purpose, stemming will do just fine. We can then print out the articles to see what they look like. So you can see we've got 100 different items. Each item is one of the articles that's been tokenized and cleaned up. The next step is to create a dictionary. So this is going to be a dictionary of every unique word in our dataset. To do this, we use corpora.dictionary and then reference our articles dataset. We can print this out and see we're left with 8,693 unique tokens. These are the number of unique words in our dataset. We then want to create a document term matrix. So when we've done vectorizing in previous lessons, this is what we're doing here. It's just a different way of doing it. So we're using a different package. So we create our doc term matrix and then we use our dictionary.doc to BOW, which you'll remember is bag of words, and then we reference our text for each of the text in our articles. So it will go through each of the items in our list of articles and create a bag of words and then join this together. We can print this out to see what this looks like. So we can see this has been fully vectorized. There are no words left in here. It's just numbers, which is going to be perfect to feed into our LDA model. To get started, we'll set the number of topics that we're interested in pulling out as 2. We can then create our LDA model using the gensim.models.lda model. The arguments required for this are corpus, which is our doc term matrix, ID to word, which is our dictionary, and specifying the number of topics that we want. We can then run LDA model.printTopics and specify the number of topics we want to print out and the number of words for each topic. And these are going to be the top most important words for each topic. So the first one, the most important words for that topic, is said, Mr. Trump, won, state. And for the second topic, Mr. said, would, state, Trump. So if you remember, we're looking at news articles here. Unfortunately, these topics aren't super informative, so it might be that we need to change the number of topics, which we'll see how to optimize in a future lesson, or we might need to clean up our dataset a little bit more, or sometimes there just aren't that many topics in the data, and it'll take a little bit of exploration to figure that out. Next, we'll move on to a different method of looking at topics that might help us pull out something more interesting. Latent semantic analysis rests on two ideas. The first is the distributional hypothesis, which states that words with similar meanings appear frequently together. The second idea is singular value decomposition, which we'll abbreviate to SVD. SVD recreates text documents into different vectors. Each vector expresses a different way of looking at meaning in the text. The vectors can be expressed by the following equation. M is our document term matrix, where our rows are each individual document and our columns are our terms. The values just express whether this term is in this document. U is a document topic matrix, so instead of our terms, our columns are our topics. Sigma is a vector, where the values express how much each latent topic explains variance in the overall data. And VT is our terms document matrix, where our rows are our topics and our columns are our terms. The small t just means this is transposed. SVD is a method of dimensionality reduction. The vectors can be used to identify similar words and documents via clustering and similarity scores. So let's see what this looks like and open up our notebook. So we're going to be following on from where we left off on our LDA model. To run our LSA model, we're just going to need to import this function. So from gensim.models, we import the LSI model. LSI and LSA are often used interchangeably, it just depends which kind of field that you're coming from. We then create our LSI model, and the code is very similar to the LDA model. So we reference our corpus, which is our doc term, our ID to word, which is our dictionary, and then the number of topics, which we specified earlier, which is going to be 2, is num topics. So we run that, and then to get our results, we print our LSA model.printTopics. So here we've got 2 topics, and we can see that they do slightly differ from when we ran the LDA model. So for our first topic, the most important words are Mr., said, Trump, state, would. And for our second topic, the most important words are Mr., Trump, said, Saudi, and wait. Let's now move on to how we can optimize the number of topics. To determine the optimal number of topics, we can use something called coherence scores. To start using these, we'll just need to import the function. We're also going to be importing the matplotlib as we want to do some plots of these coherence scores to determine the optimal number of topics. So we're going to create a for loop where we're going to iterate through different numbers of topics and then put these coherence scores into a list for us to inspect. So the first step is to create 2 empty lists, one for our coherence values and one for our models. We then specify the minimum topics we want to run and the maximum topics. Here we're using the minimum topics as 2 and the max as 11, but these can be any numbers that you like. We then create our for loops. So for num topics I, in the range minimum topics to maximum topics plus 1 to make sure that that maximum number is included. We then create a model where the number of topics changes for each of the runs in the for loop, starting with the minimum topics and going all the way up to the maximum topics. This model is then appended to our model list if we want to check it later. We then run a coherence model. This takes a few arguments: our model, our original text, which is our articles, our dictionary, and the coherence. So here we're using C_V. These are our coherence values. We then append these coherence values to our empty list. And we can get the coherence values using coherence model.get_coherence. Once we've run through this for loop and we have a list of coherence values, we can plot this to determine the optimal number of topics. So we do plt.plot, and then on our x-axis we're having a range from the minimum topics to the maximum topics plus 1. And then on the y-axis is the coherence scores. We're looking for a high coherence score, so when we plot this figure, we can see that the highest value for the coherence score is when we have 3 topics. We can then create our final model using 3 topics. So we create our final num topics, which is 3, and then we just create another LSI model using this final num topics. We can then print out our results and inspect how the different words for each of the topics comes out. It's important to note as well that sometimes the most mathematically accurate number of topics isn't always going to be the most valuable for your business. So for example, you can see here that if we had a number of topics set to 11, this would also have quite a high coherence score. However, 11 topics might be quite difficult when you're explaining to stakeholders what the different topics mean and what they're about. So sometimes it is worth manually checking how the different topics look when you're using a different number of topics. And you can use the coherence scores as well as your intuition and your knowledge of the project that you're working on and the business that you're working in and the people that you're working with to influence the number of topics that you decide to go with in the end. If you choose a value that's not the most optimal in terms of something like a coherence score, but it makes a lot more sense to you and your business, that's absolutely fine. You can go with that and no one's going to pull you up on that unless it is a really incoherent model. So it's just about finding that balancing act. But once you've run this a few times, you'll definitely get the hang of where that balance lies.